Hello viewers, welcome back to the course on scientific computing using Matlab. So, in the previous lecture we have discussed the power methods and shifted inverse power method to find out the eigenvalues of a given matrix. So, today we will continue from that. So, in the previous lecture we have discussed that what is the meaning of power method. So, we know that the power method gives you the dominant eigenvalue and eigenvector. Then we have discussed the shifted inverse power method. So, that is used for finding the A minus alpha I inverse. So, I have taken the matrix this one. So, we are finding the eigenvalue of this matrix, and then with the help of this one we are able to find the eigenvalues. So, I know that the eigenvalue of this will be 1 over lambda j minus alpha, where alpha we have chosen, and from there I can find the value of. So, this is my mu. So, based on this one I can find the value of lambda j. So, from here I can write that 1 over mu is equal to lambda j minus alpha, and from here I can find lambda j is equal to alpha plus 1 over mu. So, this way we are able to find the value of any eigenvalue of a matrix A. Now, the question comes that how we can choose this alpha, because in the previous lecture we have discussed that the alpha should be close to lambda j, whatever the eigenvalue we are finding. But the question is that we do not know what is the lambda j. So, if we do not know the lambda j, then how we can choose the alpha that should be close to lambda j. So, this is the another problem. So, that will taken care by the Gershgorin. So, before that I will just want to do the one example. So, let us take one example. So, I have a matrix A. So, I take 0, 11, minus 5, minus 2, 17, minus 7, minus 4, 26 and minus 10. So, this is my matrix and I want to find its dominant eigenvalue or eigenvector. So, in this case I apply the power method. So, let us do the apply the power method. So, let me choose, first I choose the x naught, the initial point. So, it can be any value you can choose. So, let us start with simply 1 1 1. So, this is the initial point. Then I want to find what will be the A into x naught. So, if you see from here, this is 0, minus 2, 17, minus 7, minus 4, 26, minus 10 and then 1 1 1. So, that is the vector, and that I multiply this with x naught. So, from here if you see I will get, so 1 11 minus 5. So, this will be 6 and this I will take. So, minus 2 and minus 7 minus 9 and minus 17. So, it is 8 and this is 26 minus 14. So, it is 12. So, from here I will get this value. So, and we know that the A x naught was my y naught. So, this is my y naught. So, this is y naught. You can write it as y naught. Now, what I do is that I want to make this y naught a normalized vector. So, from here what we do, I will choose the largest value in this, the component of this. So, that is my largest value 12. So, from here I will write my y naught is equal to, I will choose the 12 and then take the 12 outside. So, from here inside I will get 6 by 12, 8 by 12 and 1. So, from here I will get this value. So, this is 1 by 2, this is 2 by 3 and then it is 1. So, from here you see that, so this becomes 12 into this vector. So, I will call this vector as x1 and we call this as c1. So, from here I can write my y naught is equal to c1 x1, this one, where x1 is a normalized vector. So, now from here, so this is my step 1. Now, we choose step 2. So, from step 2 I will do a and now I will multiply by x1, this is a normalized vector. So, from here I will get my a is again the same matrix and then from here I choose 1 by 2, it is 2 by 3 and 1. So, if I multiply this one, from here I will get 11 by 2 minus, it is not 11 by 2, it is 2 by 3. So, it is 22 by 3 minus 5 and this I multiply here. So, it is minus 1 because half will cancel out with 2, minus 1 plus 17 to 34 by 3 minus 7 and in the end I will get minus 2 plus 26. So, it is 52 by 3 minus 10. So, if you choose this one, now from here I can find this. So, it is 15. So, 22 minus 15 is 7. So, it will be 7 by 3. Then if I do this one again taking the 3 LCM. So, it is minus 1 and minus 7 minus 8 and 3 times. So, minus 34, 24, 34. So, it is 10 by 3 and then it is minus 12, 36 and 52. So, it is 16 by 3. So, this is my vector I am getting and that is equal to y1. Now, if I choose from here, so my y1 is 7 by 3, 10 by 3, 16 by 3. So, now I find the component which is the largest in magnitude. So, largest component is this one because 16, 10 and 7 all are divided by 3. So, this is the largest component. So, I will take this largest component out. So, this will be 16 by 3 and I will get 7 by 16 inside because I am dividing by this one. So, 3 will cancel out. I will get 10 by 16 and this is 1. So, from here you can see from here that this becomes my C2 x2. Now, I want to find that in the previous one you can see that my C1 was 12 and now the C2 is 16 by 3. So, how will find the error? So, error at each step, because we have to find the error at each step. So, what I will do that I can find the error in from the two ways. One is that I can find my Ck minus Ck minus 1 the magnitude. So, this is the value I am finding. So, like C2 minus C1 I will find out this one. So, that is the error in, you can say that the absolute error in lambda or C, whatever we are able to we are going to find, that is the eigenvalue. So, this is the one error I can find, and other one I can find the eigenvalues error in the eigenvector. So, in the eigenvector I will find x 2 minus x 1 modulus and then the maximum. So, it is a L2 norm I will find out. So, from here what I am doing, I am taking the x 2 minus the eigenvector will got in the previous step. So, that is x 1, taking the magnitude and then find the maximum value. So, then this is called the L2 norm of the given vector. So, this we can take from here. So, based on this one, that how much this error is. So, I can take this error as E1 and this error as E2. Now, from here I will find the maximum error. So, maximum of E1 and E2. So, now if the maximum of E1 and E2 is greater than the tolerance. So, tolerance maybe I can define 0.0005. So, if this is greater than tolerance, then we keep continuing with the iterations and till this maximum error is less than tolerance. So, if it is becoming less than tolerance, then we will stop, less than or equal to. So, then in that case we will stop, and that is whatever the value we will get, that will be our lambda, the eigenvalue, and the corresponding eigenvector. So, in this case we have able to find these two steps. Then I can take next step 3. So, that will be a x 2. So, from here a x 2 is this one, then I will substitute, I will find whatever the value I will get y 2. So, that will be a that will be equal to C 3 x 3 and so on. So, I will keep doing this one. So, we will find out that in the Matlab code, that in how many iterations we are going to find the solution, but this is the algorithm, this is the way we can find the solution. So, that we will find out in the terms of when we will do the coding in the Matlab. So, this is the way we can find the dominant eigenvalue. So, this is the example we have done. Now, we are going to start the next topic, and that is a very important topic. So, this is called Gershgorin circles. So, this is a basically you can say that it is a theorem. So, what this theorem is saying? It says that the modulus of the largest eigenvalue of a matrix cannot exceed the largest sum of the moduli of its elements along any row. So, it says that the modulus of the largest eigenvalue of the matrix cannot exceed the largest sum of the moduli of its element along any row. So, what is the meaning of this? It says that if I take a matrix A, the same matrix we can take. So, it says that 0, 11, minus 5, minus 2, 17 minus 7 minus 4, 26 and minus 10. So, in this case what I will do, I will find the sum of the first row. So, I can write from here that A11. So, from here I can find the first row sum. So, that is equal to 0 plus 11 plus minus 5 modulus, because it gives the modulus value. So, it is 16. The second row, it is minus 2 plus 17 plus minus 7. So, that is 2, 79, 26, and the third row is, that is equal to minus 4 plus 26 plus minus 10. So, it is 26 plus 4, 30 and it is 40. So, from here it says that if I take any eigenvalue, so that is always less than equal to 40. So, that is the, so modulus of the largest eigenvalue. So, from here I can even write lambda maximum. So, that will be always equal to 40. So, from here you can even define the range, then the max will be minus 40 up to 40. So, from here we can see that all the eigenvalues of this matrix are lying between minus 40 to 40. So, that is the upper bound for, that is the bound for lambda. So, this is the way we can find out. So, let us do the proof of the theorem. So, let we choose the matrix A n cross n and let lambda r be an eigenvalue with corresponding eigenvector, that is I will choose x r. So, from here I can write that this is A x r is equal to lambda r x r. So, that is the definition of the eigenvalue, that how we can find the eigenvalue. Now, this x r you can write, it is a vector, it is a column vector. So, that is basically x 1 r, x 2 r, x l r, x n r. So, that is the component of this vector. Now, let x l r modulus value. So, this is the factor, is the largest component of x r in magnitude. So, suppose this is the largest component, like in the previous one we have seen like 16 by 3 earlier, 12. So, this is the largest component. So, suppose this is the largest. So, that is why L has been taken. So, this is the XLR, means this is the rth vector and L is the largest component of this one. Now, from here, now we can multiply this XR by this matrix. So, A is my matrix. So, I can write my A XR can be written as, so first component x1r and then the first column of the matrix. So, that is A11, A21 up to AN1 plus x2r, A12, A22 up to AN2. Then XLR, so the component will be A. So, it is 1R, 2R, so it is 1L A to L up to A and L, because this is the L is the largest component we have taken, and in the end I will get X n r. So, that is A 1 n, A 2 n up to A n n. So, this is how we can multiply the matrix A with the X r. So, and that is equal to lambda r X r. So, this is we can write, I will call it equation number 2. So, from here now if I write this one, so I can write this in the terms of A I, you can see that I changing 1 into x 1 r plus A I 2 into x 2 r, A I L into x L r, A I n into x n r, that is equal to lambda r x r for all I. So, I is moving from 1 to n and r is also moving from 1 to n. So, this is we have taken corresponding to lambda r. So, okay, so I will take this part on. So, we will consider it only up to this. So, this is true for all this one. So, that is the equation number 3. Now, what I do is that this is the maximum element I know in terms of magnitude. So, we divide equation 3 by x L r. Okay. So, I will get A I 1 x 1 r by x L r plus A I 2 x 2 r over x L r plus A. So, this is I L, only I will get I L, and in the end I will get A I n x n r divided by x L r, and from here I will get lambda r, and this is I am dividing by whole. So, this is again x 1 r by x L r 1, in the end I will get x n r over x L r. So, this is I am getting, that is equation number 4. Now, if I choose, so, and this is true for all rows. So, that is I is moving from 1 to n. Now, for any ith row, so I just take any ith row, for any ith row, first I choose ith row and then taking modulus value. So, I will get lambda r, and then this is x, any x I r divided by x L r, and then I am taking the modulus value. This can be written as again, so this is A I 1 x. So, this is I have taken for any ith row. So, this is x 1 r over x L r mod all this value up to A I n x n r by x L r modulus. So, this value we have taken. Now, from here we know that this can be written as lambda r into x I r by x L r, and this one I can take as a apply the inequality, the triangle inequality. So, this can be written as less than equal to. So, from here I can write this as a I 1 x 1 r over x L r plus AIL and then AIN modulus XNR over XLR. So, this one I have taken. Now, I know that all this component, if you see, then all this component, this component, this component, this component all are less than equal to 1, because we have chosen this this XLR is the maximum element. So, this all values will be less than 1. So, from here I can write that my lambda r. So, this one I can, so this is true for all I. Now, from here I can write that my this can be written as AI2 AIL up to AIN. So, from here I can add that this lambda r is less than equal to summation modulus A I. So, I am taking I and 1 2 3. So, this is changing. So, this is I can take as a j, and j is moving from 1 to n. So, this is we are taking from here. Now, this is true for all eigenvalues. So, this is true for all eigenvalues. So, from here I can write that. So, I can write from here that lambda r modulus can be written as less than maximum of this one. So, this is also true. And from here I can write that lambda max, well, we always less than this. Because this is true for all. So, that is true for all eigenvalues. I will choose a maximum eigenvalue in the modulus. So, that will be also less than equal to this value. So, that is I can write as a fifth. So, from the fifth we can say that whatever we want to show, that the modulus of the largest eigenvalue of the matrix cannot exceed the largest sum of the corresponding row sum, modulus of the row sum. So, in this case I am taking the modulus of each element in the row, and then I am taking the summation, and then we are taking the maximum of all this summation. So, from here I can say that my eigenvalue, maximum eigenvalue will be always less than this one. So, this is upper bound for the lambda x. Upper as well as lower. So, from here you can write that this is bounds for lambda max. So, let us stop here. So, today we have started with some example to find the dominant eigenvalue using Powers method, and then we have to find the value of alpha in the case of shifted inverse method. We are taking the help of Gershgorin theorem. So, that we have discussed today. So, in the next lecture we will continue from the Gershgorin. So, I hope you have enjoyed this one. Thanks for watching. Thanks very much.